Oh, yes. Good.
Okay, we're recording. We're recording. I got recording on top. Okay.
Okay, shall I start now?
Welcome to the New York City Category Theory Seminar. Nicholas Meadows is going to be talking on higher homotopy operations in infinity one categories. Go right ahead.
Okay, so to begin my talk, I would like to start by explaining some basic concepts from topology. So first of all, I'm going to explain the fundamental group. So a path on a space X is a continuous map from the unit interval to that space X. A loop is a path with F0 is equal to F1. And we say that two paths are homotopic if and only if they can be continuously deformed into one another. So as an example, here I have a continuous deformation from this like bold black path on the, I guess, going kind of upward to one at the bottom there. And you can kind of see the stages that one goes through to kind of continuously deform one to the other. These are both paths between kind of the points that the kind of the corner point. So the fact is that homotopy is an equivalence relation, and the fundament.
Somebody else has there and is not muted.
Yes. So the fundamental group. Shall I continue?
Please.
The fundamental group.
Everyone to mute, please. If everyone besides the speaker could mute, thank you.
Okay. So the fundamental group of a topological space is denoted. Okay, somebody's like, this is. I can hear a lot of background noise somewhere.
You can mute, Nicholas, as the leader, Nicholas, you can mute pi 1 of S1. Oh, okay. You did it right. Good.
Okay, so the fundamental group of a topological space X is denoted pi 1 of X, and it's one of the most important and basic objects of algebraic topology. Basically, pi 1 of X is homotopy equivalence classes of loops on X with a fixed base point. And you can think of the base point as the value of F0 equals F1. Multiplication of loops, how we impose the group structure on this set is done by precomposing with the pinch map. So we can think of the two loops F and G as given by a map from the figure 8 to the space. And I guess the loop F is indicated in blue and the loop G is indicated in red. And we precompose that with the pinch map, and the pinch map is kind of the map, the map depicted on the left-hand side of this. As an example, pi 1 of Rn is isomorphic to 0 because every loop can be contracted to, in Rn can be contracted to a point. Pi 1 of S1 is isomorphic to the integers. And the elements of pi 1 S1 corresponding to n in Z is the homotopy equivalence class of a loop that goes around the circle n times. And of course, if n is positive, we think of it as going in the opposite direction as if n was negative. More precisely what a homotopy is a homotopy of maps. All maps are continuous because we're dealing with topology here. Is of maps fg from y to x is a map from y times the unit interval to x such that h restricted to 0 is f, h restricted to 1 times x is g. We can use this to define the higher homotopy groups pi k of x as continuous maps from s to the k to x modulo the relation of homotopy equivalence. For k equals 2, multiplication is given by precomposition with the suspension of the pinch map. And we can kind of think of the suspension as we kind of glue two cones over the suspension of a space as we kind of glue two cones over the space together to get the suspension of the space. And we can, in general, we have that the suspension of s to the k is homeomorphic to s to the k plus 1. So we can define multiplication for pi k of x by precomposing with some suspension of the pinch map. So fact, we have pi 0 of s to the k is isomorphic to the integers, which is isomorphic to pi k s to the k. And actually the generator of pi k s to the k is obtained by applying suspension k minus 1 times to the generator of pi 1 of s1, which is just the loop that goes around s1 once. For I between 0 and k, always pi I of sk is isomorphic to 0. And one simple case that you can use to visualize this is imagine a loop on a two-sphere. Any loop on a two-sphere can just be contracted to a point. The calculation of pi I of s to the k, though, for I greater than k is one of the most difficult and central problems of algebraic topology. As an example, pi 3 of s2 is isomorphic to the integers, and the generator is a certain map from S3 to S2 called the Hopf map. So the way that so SK, recall, is given by the following formula in k plus 1 dimensional space. So S3 is something in 4-dimensional space, so it's difficult to visualize. The way that one can visualize this is to use what's called the stereographic projection. So the stereographic projection is kind of a homeomorphism from the k-sphere to r to the k union a point at infinity. And it takes the north pole to the point at infinity. And it takes p in sk minus the north pole to the unique point p prime of intersection of the plane x not equals 0 and the line between p and n. So as an example, here we have, in the case, the stereographic projection of S1 onto R1, the point P gets taken under stereographic projection to the point P prime. And so we can visualize the Hopf map by considering it as a map from R to the K union a point, R to the 3 union a point at infinity to the 2-sphere. And the inverse image of the circles will always be tori under this map. So, and this kind of picture that I have here is kind of a picture of what the inverse image of what some of the circles on the 2-sphere look like under the Hopf map, at least using this identification of S3 with R3 union a point at infinity. So the thing is that, as I said, the Hopf map is kind of like almost the simplest non-trivial example of pi I s to the k where I is greater than k. So what our talk is going to be about is how can we produce elements in these groups pi I k by kind of producing them from sort of smaller, lower dimensional maps. And there's a couple of notions that we're going to, and the first way we can do this is through the notion of Whitehead products. So the P plus Q minus 1 sphere is homeomorphic to the boundary of IP times IQ, which can be identified with a kind of push out in spaces of basically where the boundary of IP times IQ, IP times boundary of IQ with boundary of IP times boundary IQ kind of along the boundary of IP times boundary IQ. Now, if we collapse the boundary of IP times the boundary of IQ to a point, then we get a map to IP with the boundary collapsed to a point, wedge with IQ with the boundary collapsed to a point. And this is the same thing as kind of a wedge of a P sphere and a Q sphere, because that's just a fact about from algebraic topology. If I take the IP and I take the boundary and identify it to a point, then I get a P sphere. Here I is the unit interval. Sorry, I should have said that. The Whitehead product takes classes which are represented by S to the P to X, G from SQ to the X, to the class which is represented by precomposing with this collapse map that I've defined. And so as an example, let's consider the boundary of I2 times I1. The boundary of, which is just going to be the boundary of a cube. So I've kind of put I1 in blue and I2 in red. And then I2 times the boundary of I1 gets identified with two kind of disjoint copies of the square, and boundary of I2 times I1 gets kind of identified with I guess the second picture, except you should probably think of the I guess the sides going I guess going back as kind of filled in. So if we collapse the boundary of I2 to a point, then in the first picture we get just a two sphere, and if we collapse the boundary of I2 in the second picture to a point, we just get a loop. So basically the pinch map in this case would be somehow like a map from and this is kind of like the lowest kind of dimensional idea of what the collapse map is going to look like. It's going to be a map from the boundary of that cube to the union of S2 and the loop. So a more sophisticated way of producing new elements in the homotopy groups of spheres. Does anybody have any questions, by the way? Sorry.
This is going, sorry, let me be really basic. When you say a new element in the homotopy groups of spheres, like, can you just define what that means? Like,
well, it means that I want to produce, okay, so as an example, let's go back to this thing here. I have a group homomorphism from pi p x times pi q of x. I look at the image of something under that homomorphism. That gives me sort of, I guess, a new element. That gives me a new element that I didn't know before by looking at the image under that homomorphism. That's sort of what I mean.
So it's just concretely you're generating an element of this other thing from some map so you can get your hands on it as opposed to just sort of abstractly knowing it.
Yes, yes. That's the idea, is we have ways, well, actually later on, one of the points of this talk is going to be to see that we can actually like apply certain operations to get basically to very, very simple homotopy classes of maps to get basically every element of every homotopy group. That's what we're going to move towards in this talk.
Can I just ask, there's nothing ensuring that this Whitehead product is injective, right?
I don't think it would be. I really don't think it is.
So just defining an element in pi p plus q minus 1, there might be more than one way of doing that.
As a Whitehead product, yes.
Okay.
I can't think of any examples off the top of my head, but yeah, I think the Hopf Map. Sorry.
I don't imagine it's symmetric. In other words, commutative.
No, I don't. I mean, well, how would it be commutative? Well, it can only be commutative if P equals Q, right?
Right. Well, okay. Right. I don't know. It could be.
Oh, actually, yes. Well, I'm not sure if it's commutative.
Okay.
I don't know. I don't think so, though. I would strongly doubt it. I mean, these pi p's are going to be abelian for p greater than 1.
Right.
That's just a theorem but I don't know that, but that doesn't necessarily have to do with the, yeah, that doesn't necessarily.
Oh, good.
Okay. Shall I continue?
Please, it's very interesting.
Okay, thank you. Thank you for saying it's interesting. So a kind of a more complicated way of producing elements in the higher homotopy groups of spheres is the classical threefold Toda bracket. So suppose that we have a string of morphisms such that each composite is of spaces such that each composite is null homotopic. So it can be kind of contracted. So these are like maps that can be contracted to a point. Then I hope you can see this, but basically one way of realizing a null homotopy is as a map from the cone over the space to, so basically the null homotopy H1 is given as a map from the cone over x2 to x0. The null homotopy H2 is given as a map from the cone over X3 to X1. And these guys glue together to give a map from the suspension of X3 to X0. And this is this actually gives a map, an element of the space of maps between the suspension of X3 to X0. And this is called the threefold Toda bracket. Now, I have a couple of comments that I'd like to make. So first of all, like the space of maps is, I guess you're going to need to have some kind of local compactness thing to actually make sense of this, but all the spaces we care about are CW complexes, and they'll certainly satisfy that. So basically the space of maps is continuous functions from X3 to X0 equipped with this topology called the compact open topology. So another kind of general comment is if I put the space of maps from the path components of the space of maps from the suspension of X3 to X0 is always going to be isomorphic to pi1 of the space of maps from X3 to X0. And this is just a fact about suspension. Of course, if I iterated the suspension, so I had suspension to the K, I would get an element of map from the suspension of K of X3 would give me an element of pi K of the space of maps. And so this is called the threefold Toda bracket. Now, the thing is that if Xi was equal to Sk of I, then I would get, for all I, then I would get a map from the suspension of a K sphere to a K sphere. And of course, the suspension of a K sphere is a K+1 sphere. And so because of this, I can use this procedure to construct new elements in the higher homotopy groups of spheres. Now,
could you just go back up for 1 second? What is the relationship between this threefold Toda bracket and the product that you had before?
They're kind of defined, the definitions are independent to one another, but we will see later on how they play kind of a role in generating what we'll see later on is that they'll be kind of like elementary operations that we can use to generate new elements of higher homotopy groups of spheres. So these are just two ways of producing new elements of homotopy groups of spheres from kind of known things.
Right, but so far they have no connection whatsoever. The only thing is this thing seems to be this three Toda bracket seems to be only generating things in pi1.
Well, it's pi1 of the space of maps.
So if you make X3 into a higher sphere, then you have then
I have a K, and it goes from a K sphere to K+1 sphere, because remember the suspension of a K sphere is homeomorphic to a K+1 sphere.
Good. Okay, thank you.
Yeah. So one kind of weird thing about Toda brackets is that it actually depends on the choice of null homotopies we make. So if we choose different null homotopies, we get different values for the Toda bracket. So we also have a fourfold Toda bracket. And in this case, we think of this, recall that I talked last time about the space of maps between X3 and X0. We're going to actually think of this as happening in the space of maps between, let's say, X4 and X0. This kind of picture that I'm going to draw. So suppose that we have a string of maps of 4 maps such that each composite is null homotopic. And let's suppose that the element of the element corresponding to the Toda bracket, I guess as an element of pi naught vanishes. Then what we can do is we can define the fourfold Toda bracket. This only exists if the threefold Toda bracket of the first three and last 3 maps vanishes. So we can think of the threefold Toda bracket as kind of a loop, which I guess in this space of maps, which is kind of the boundary of the front face. Now, the fact that this is null homotopic means that we can extend this map from the boundary of a square to a map from the square to this space of maps. And the back face is kind of defined analogously. And this is so and I guess the left face of this is H, which I labeled H1, H3, is kind of going to be just kind of a product of homotopies in some sense. Then the remaining two faces are just zero. So they're just like the zero map, basically from a square to a point zero. And this determines a map from a two-sphere to the space of maps because the boundary of a cube is homeomorphic to a two-sphere.
Okay, good.
Okay. So now the question is how can we interpret this all in terms of categories? So there's a two category such that the zero cells are spaces, one cells are continuous functions, and two cells are homotopies between functions. So the vertical composition of two homotopies is given by the following formula here. Oh, there's another participant. Just hold on a second. Admit. Yes. Sorry, there's just another participant that showed up. So, and then the and then there's also a horizontal composition of two cells, which is given by the following formula. And so in most of my pictures, I've written, I guess, a subscript 0 for under composition. Whenever I don't have a subscript, I just mean ordinary composition of continuous functions. So that's how the horizontal composition is defined. So, okay, so if we look at two cells, which sort of correspond to these homotopies, then the Toda bracket can be identified with the following expression. And in this expression, we have a horizontal composition with a, I guess, an identity two cell of F0. So that's just like the identity homotopy from F0, the map F0 to itself. And we also have a horizontal composition of this H1 inverse with the identity homotop two cell from F2 to itself. And we take the vertical composition. And we can check that this actually is a formula for the Toda bracket that we mentioned. So the thing is that we're only interested in the homotopy class represented by this Toda bracket, right? Because we're interested in elements in homotopy groups of spheres. And the value depends only upon the homotopy classes as well of H1 and H2. So if I had a higher homotopy between the homotopy H1 and H1 prime, this would basically give the same element in the higher homotopy groups of spheres. So thus we should replace the two cells in our thing with homotopy equivalence classes of homotopies. And in this case, we get the structure of a category enriched in groupoids. So the thing is that if we wanted to represent the fact that, let's say,
what you just said was that that's called a 2-1 category, where the two cells are only isomorphisms.
Yes, that's, well, if you replace the two cells with homotopy equivalences of homotopies, then yes. But I mean, okay, so we usually, I guess we've used the terminology structure of a category enriched in groupoids.
Okay,
to kind of,
right. Okay.
Because I mean, the way that you get a 2-1 category is you look at you look at categories enriched in categories or something like that, right?
No,
Or
that's a regular 2 category.
That's a regular 2 category, yes.
Right.
But this, so regular 2 categories, so we get the thing that you refer to as a 2-1 category by looking at I guess category objects in groupoids or something like that. Or maybe it's the reverse way around.
I know, I like the way you read it. Categories enriched in groupoids. That makes sense. The two cells are only isomorphisms.
Mm-hmm. Yeah.
Well, I also want to check one thing. if it's okay.
Okay.
When you went back a moment ago, you wrote a formula for the horizontal composition. I just wondering, is there a intuitive geometric description of it? Because the vertical is just compose the homotopies, but the horizontal, I just couldn't parse the formula in real time.
Okay. Okay. Sorry about that. So what I can think of is, okay, so the first thing I do is I look at the homotopy from F to G, and then I compose that homotopy, which is, so that homotopy is given by a map from F times the unit interval to Y. And then if I compose that with H, I get a homotopy from H composed with F, G composed with H. Okay, that's what the first thing, the H composed with C corresponds to, okay? Now, what I do is I take the composition of G, is I take the G times the identity, and I compose that with the homotopy between H and L, right? And then I get a homotopy between G composed with H composed with G, and L composed with G, okay? So then what I can sort of think of it as is what I do then is I compose this homotopy from this. Now I have two kind of homotopies. I have one from F composed with H composed with F to H composed with G, and G composed with H composed with G, L composed with G, and then I kind of take the horizontal composition of them. So now I get a homotopy between H composed with F to G to L composed with G.
Thank you.
Okay, thank you. I hope that was that I answered that okay.
I think that's why we do horizontal composition of natural transformations. In some sense.
Yeah.
Anyways, there are two cells.
Yeah.
Okay, good.
Well, natural transformations come from topology, so that's not a surprise there. Originally, that's where they came up, and then they went into all these other things later on. Yeah. So we get so anyway, to represent the fact that we have a null homotopy of P F3 F2 F1. That was, remember, if we have we have a string of 4 maps. In the definition of fourfold Toda bracket, we would actually need to consider 3 cells to represent this null homotopy. And because of that, we'd have to work with categories enriched in 2 groupoids. Now, to study higher order Toda brackets, we would have to work with categories enriched in n groupoids. And my one kind of comment about this is there are actually, for some applications, it's actually desirable to work with categories enriched in groupoids. But for the kind of applications that I have in mind, I'm actually going to work with a different thing, which is a model of which are simplically enriched categories. I should also mention, when I mean higher order Toda brackets, I've defined 4-fold Toda brackets, 3-fold Toda brackets. There's also a notion of 5-fold, 6-fold, etc., etc. And these get and to define those, that's when I would need these categories enriched in n groupoids. So what I'm going to do now is I'm going to kind of talk a little bit about simplicial objects in categories for a little bit. So, and this will help me to explain kind of the model of higher categories that I'm going to use in my work. So delta is the category of ordinal numbers and order preserving maps. The morphisms are generated by the unique order preserving map from n to n plus 1, which omits I, for I equals 0 to n plus 1, as well as the unique order preserving map S of I, which hits I twice. And such a thing exists for I equals 0 to n, for S of I. So a simplicial set is an object in the functor category from delta op to set. And it can be specified by a collection of sets xn, n in the integers, along with certain maps di from xn to xn minus 1, sj from xn to xn plus 1. And notice here, because we're taking a functor from the opposite category, that's why we're getting things in the opposite direction, kind of. So these guys will also specify, these also are, these maps, these DIs and SJs have to satisfy certain simplicial identities, which I've listed here. And I guess you can verify by hand that the maps, the D uppercase I and this S uppercase I satisfy analogs of these, but it's kind of tedious and it's a fun exercise, but I don't want to like, you know, detract from the talk. But you have these kind of combinatorial identities. And what this kind of simplicial sets do is they're kind of abstract models of abstract simplicial complexes. So a simplicial complex we can think of as a space that is made by gluing together what are certain objects called n simplices. The zero simplices are kind of points. The one simplices are line segments. The two simplices are triangles. The three simplices are tetrahedrons. And the n simplices, I guess, are sort of higher dimensional analogs of these. So what we think of the simplicial set as is it's kind of abstractly, we're keeping track of kind of the combinatorics of how these simplicial complexes are kind of built up from their simplices. So xn is the list of n simplices. That's what we think of it as. And we think of di sigma as the simplicial complex obtained by deleting the ith vertex. Now, an important kind of note about simplicial complex is although it's not shown in this picture, we think of these kind of line segments as directed. So, and we think of the vertexes as sort of ordered. And I guess the vertex, let's say, the line segment will always kind of go from let's say from a vertex I to a vertex I plus j, where j is something greater than 0. And so the thing is that for every simplicial set, we can kind of realize it as simplicial sets are models of spaces. So there's always going to be a unique co-continuous functor that takes I guess a sigma, sigma and xn to sort of the standard n simplex. Sorry, that's not quite right, but basically it's basically the idea is that each simplicial set can be written as a co-limit of its simplices, right? And there's kind of a unique co-continuous functor that takes each n simplex to the standard n simplex as a space. And this is basically this is basically the thing that's given by this formula abstractly, and it'll correspond, I guess, in the low dimensional cases to these things like tetrahedrons and triangles and so on and so forth. So the idea is that simplicial sets are models of spaces. And specifically spaces made up from these kind of simplicial complexes like. So a map of simplicial sets is a collection of maps from xn to yn that sort of respect these simplicial identities. They respect the face and degeneracy maps. And kind of an example of an abstract simplicial complex or an abstract simplicial set is the nerve of a category. So if I have a category C, then I can form a simplicial set whose n simplices are strings of n morphisms. And for each I between 0 and n, the ith face map is basically the string that's obtained by concatenating fi and fi plus 1 and leaving everything else. D0, just you delete the first morphism. Dn, you delete the last morphism. And more generally, we often want to talk about simplicial objects in an arbitrary category. And this is an object in the functor category, the category of functors from delta op to our category C. And it can be specified in a similar manner by specifying the face and degeneracy maps, as well as the set of n simplices x, as well as the choices of objects xn in this thing corresponding to choice of n simplices. So rather than work with categories enriched in n groupoids, we're going to work with simplically enriched categories. where the morphisms have the structure of, and this is like where we think of the morphisms having a structure of a simplicial set, rather than rather than just having a set of morphisms.
Do you put restrictions on your simplicial sets? In other words, you say it should only have non-trivial n+1 dimensions?
Non-trivial n+1.
In other words, if you're going to n groupoids, then I mean, simplicial sets have
yeah, well, you can do that, but the idea is that you want to consider because your simplicial enrichment is supposed to capture the idea of these n-fold Toda brackets for arbitrary these n-fold Toda brackets for arbitrary n. You don't really want to put a bound on it. You want to have you kind of have like something like an omega category or something like that. That's what you want. So you don't want to put a dimension, to put a bound on it. You want to have all the possible information used to define these higher homotopy operations.
Oh, so I didn't know what you meant by n groupoids. N groupoids, n can be as large as you want when you say n groupoids. So fine. So then your simplicial sets can be as large as you want also.
Yes, because I don't think there's any way you can say there's like a bound on the number n you need of kind of like n-dimensional operations. You might need R as to kind of generate these homotopy groups, and I'll formally state the theorem about that more towards the end of the talk, if that's okay, because that's but we will get there. There's just like, but anyway. So the idea is that the simplically enriched, so there's a simplically enriched category whose objects are pointed spaces. So usually we talk about homotopy groups, we usually talk about a base point. The base point is always in the background, but to me it's like, I just almost forget about it. So the simplicial set of morphisms is given in degree n by the set of morphisms from the product of x and the standard n simplex, the formula that I wrote sort of before here, to y, and the face maps are kind of induced by face inclusions. So like what I mean by face inclusions is, I guess, okay, so let's go back to my picture here. So I guess we can sort of think of this as the vertex. So let's just look at one of these little triangles here. We can label the vertices 0, 1, 2. The ith face of that triangle is going to be the line segment consisting of, I guess, consisting of all going from the vertexes that are just not labeled I. Sorry. Yeah. And so you think of each line segment as kind of a face of this, and the inclusions and the face inclusions in the case of this triangle guy are just the inclusion of these line segments into the triangle. The zero simplices are going, this might make it a little more clear. The zero simplices in the space of maps are going to be just morphisms between x and y, continuous functions. The one simplices are going to correspond to homotopies because the standard one simplex is just the unit interval. And a two simplex we can think of as kind of a choice of homotopy f composed with g to h. And one kind of remark is that if we take the geometric realization, remember I mentioned there's this geometric realization functor from simplicial sets to spaces. This actually gets identified with the space of maps that I defined way back. If I apply geometric realization to this, the simplicial set of morphisms between x, y, I actually get something that's homeomorphic to the space of maps that I defined earlier on in the slides. So like, I guess the space of maps from x to y is just continuous functions from x to y with the compact open topology. So the three simplices we can sort of think of as kind of a choice of homotopy between the composite D1 of S, D0S. to D3s, D2s. So basically the D3, the DI of S, so if our 3 simplex is S, the DI of S is kind of the 2 simplex that's obtained, that's basically obtained by deleting the ith vertex in this picture. So what we're getting is we're kind of getting some kind of higher structure that encodes homotopies, homotopies of homotopies, etc., but in a slightly more complicated way than what we would like. Because in our previous categorical interpretation, a 3-cell would have been kind of like a homotopy of homotopies, right? So actually, it would be given by a map to the space. Basically, be given by a map from the triangulation of a cube to this simplicial set of morphisms between x and y. And a 4-cell can be given as a map from the triangulation of a cube to this space of maps from x to y. Are there any questions about this portion? No questions? Oh.
I have a question.
Mm-hmm.
So this notion of choice of homotopy reminds me of, I think, filling for can horns.
Sorry?
The can filling for a horn.
Yes, it would be the con fill-in for, yeah. I mean, like, I guess that it would be like, I guess like that, you could think of it that way. Except of course the thing is that when I talk about a can fill-in for a horn, remember that one of the faces it's not the boundary of this, but it's like you're deleting one face, right? So basically what you would say is, I guess something like, I don't know, like I've specified D2, D0, D3, D2, then there's going to be a unique guy D1 that's going to satisfy this identity. And that would be like kind of, that's what the inner, that's what the con condition, or the inner horn filler condition would kind of, or the horn filler condition would mean for in this context.
I see. Thank you very much.
Yeah. So now we kind of come to the notion of a type. Oh, more chat. Somebody's okay. So suppose that we have so imagine that we have maps of spaces. I guess sort of like so imagine that we have x2, x1, x0, x-1 are spaces, and we have basically we have maps, let's say labeled D0, D1, D2, etc. as depicted. And let's suppose that instead of having the simplicial identities hold on the nose, we're going to have them hold up to homotopy. Then we could think of this as, like, I guess, a homotopy commutative diagram in spaces. And we can kind of formulate what this means in an arbitrary simplically enriched category, but let's just think about it in terms of spaces. So what we do is we choose, so we're going to actually select homotopies between di, dj, dj minus 1 di, and we can arrange them in a way that determines a map from the boundary of a 2 permutahedron to the space of maps from x2 to x-1. And that's depicted here. So when I wrote D0 H upper script 201, what I kind of am thinking of this as is I'm thinking of this as kind of a composition, as taking a horizontal composition in our old categorical language of the identity 2 cell from D0 to itself with the 2 cell corresponding to this choice of homotopy H upper script 201. And similarly, we get kind of this, and that's more or less how we would define all these other kind of things that we arrange in this hexagon here. So the idea is that this determines an element of pi1 of the space of maps between x2 and x negative 1, which vanishes if and only if this map that we defined extends to a map from the boundary of a 2 permutahedron to the space of maps from x2 to x negative 1.
To me, it looks like a coherence condition.
Actually, the thing is that there's an interpretation of this element as an obstruction to having a coherence condition between these homotopies. So like what I can think of it as is if I can fill in this map from the boundary of a hexagon to a to an actual map from the full hexagon, not just its boundary, then actually this homotopy commutative diagram becomes a homotopy coherent diagram. And I can actually, and then there's like this theorem in topology that says that I can actually replace it with an equivalent diagram that's actually a strict diagram, where the simplicial identities hold on the nose. And that's actually one of the interpretations of the higher homotopy operations, is as obstructions to homotopy coherence problems.
My thesis title was Obstructions to Coherence.
Yeah. Well, this is a topological kind of
Right,
interpretation of that.
Right.
Yeah. So anyway, if this operation vanishes, let's consider the extension to a homotopy commutative diagram as depicted here. And what this means is we have the simplicial identities that I mentioned before hold only up to homotopy. This is also like a restriction. This is kind of like a restricted simplicial diagram though. So we don't put in the degeneracy maps, we just have face maps. So for each I less than j less than k, we have a threefold higher homotopy operation associated to the composite di, dj, dk. And this is kind of like a map from the boundary of a 2 permutahedron to this space of maps, which is kind of specified by kind of arranging all these homotopies together, like so. And it's defined kind of analogously to the previous one that I talked about on the previous slide. And if the element in pi1 of the space of maps associated with these vanishes as well, then we have an extension to the 2 permutahedron. And we can define a fourfold higher homotopy operation as a map from the boundary of a 3 permutahedron to the space of maps from x3 to x negative 1, as depicted on these slides. And you should think of these LIJKs, their existence is kind of a coherence condition, a higher coherence condition. So, so in this picture, the vertex labeled, let's say IJKL, corresponds to the composite DI, DJ, DK, DL. And these, the hexagons are going to be kind of, they're basically like, we basically pre and post compose with these homotopies that with these maps that we defined, I guess from that come from kind of the vanishing of these elements, these homotopy groups. And essentially this gives us a map. This is like the boundary of a 3 permutahedron, and this gives us a map, an element of pi2 of the space of maps. So we think of this as happening in the space of maps from x3 to x negative 1, and the homotopies are like, I guess, maps from the unit interval to that, and so on, and these higher coherence things are like maps from the hexagon to that, and so on. So, yeah. So in general, we can define the vanishing of certain n-1 fold operations, and there will be many of them, as we saw in the case of even in this lower dimensional case we just talked to, allows us to define an n-fold higher homotopy operation associated to some homotopy commutative diagram. This is an element of pi n-1 of the space of maps, which is determined by a map from the boundary of an n-1 permutahedron to the space of maps. And this is determined by that because the homotopy type, the boundary of an n-1 permutahedron is homeomorphic to an n-1 sphere. Like for instance here, like the boundary of a hexagon is homeomorphic to 1 sphere. The boundary of this guy here is homeomorphic to a 2 sphere. So now we finally get to the point, the punchline. If I have a wedge of simply connected spheres, which just basically means we're kind of gluing together a bunch of spheres along the base point, and simply connected means it's just not like a circle. It's a higher dimensional thing. All elements in the higher homotopy groups of spheres can be generated from the fundamental classes under type 2 operations by Whitehead products, group operations, and iterated composition. By iterated composition, I mean just like composing maps, like in the usual sense. So if I had a map from like Sj to Sk to Sl or something, I mean just composing these. And the group operations is just like the group operations in the homotopy groups. So I should mention what the fundamental classes are. The fundamental classes are the generators of pi k of S to the k, which I mentioned at the very beginning, how pi k S to the k is isomorphic to Z. So in each kind of wedge summand. So the thing is that the Toda bracket is kind of like an analog of these type 2 operations when we're interested in like what are called stable homotopy groups. And there was a theorem about stable homotopy groups that is sort of similar to this theorem 1 here, which came from the 70s, and it was due to Cohen. This was, and basically his theorem said that if you look at stable homotopy groups, then these then the Toda brackets kind of will and these operations that I mentioned, the Whitehead products, etc., will generate the stable homotopy groups. And this definition here is kind of like for just the homotopy groups we've talked about. So is there any questions about this part so far?
Good, go.
Okay. So now, can I ask how we're doing for time?
It's 8 o'clock now, so how about till 8:30?
Okay. Do you mind if I take like a 2-minute break?
I love breaks. I'm all for it.
Okay. Or a two
So
or
I'm
3
gonna
minute break.
pause the recording.
Okay.
I think I can do that. Recording, go.
Okay. So the next part is going to be about sort of spectral sequences. So spectral sequences are
Well,
kind
one
of.
second. Are you going to prove that theorem?
Wait.
Not that I want you to prove that theorem, but are you going to prove that theorem, or are you just going to?
I'm going to explain how it's. I might explain how it's a result later on. I'm going to explain a result about how it's proven. Which means and this will tie into spectral sequences.
Go.
Okay, so the idea is that a spectral sequence is a collection of, I guess, bigraded groups, ER. E, and here R is I guess, superscript R. So that, and usually we assume they're homologically graded, so that means that ERPQ is 0 for P less than 0 or Q less than 0. There are going to be, for each R, there's going to be certain morphisms between different parts of the grading. And basically the ER plus 1 part of the spectral sequence is going to be given as the homology of sort of these morphisms dr. So for P, fixed P and Q in big enough R, we have ERPQ is equal to ER plus 1 Q, and so on and so forth. And this, in fact, follows from the fact that basically the definition of the differential is going to go from P minus R is going to go from ERPQ to P minus R. And for R bigger than P, then this is going to be 0. So we would have ERPQ is equal to ER plus 1 PQ, and so on and so forth indefinitely. And we write the kind of this fixed value that it obtains by E infinity PQ. So we say that a spectral sequence converges to something to some group En infinity, some collection of groups En infinity, if and only if there exists a filtration of this group, so that the quotients at each stage of the filtration are kind of given by the E infinity terms. So so this is this is kind of a very complex definition. It's honestly very hard to do in a talk, but the idea, but spectral sequences, I guess you can think of them as giving kind of successive approximations to some filtration of a group that we're interested in. So this is usually like a homotopy group or a homology group, and this is like the basic tool of computing stuff in algebraic topology. One kind of spectral sequence that's very common comes from what is called an exact couple. So an exact couple is kind of an exact sequence. Let's say I star del star delta, such that del star decreases the horizontal grading by 1, and delta decreases the vertical grading by 1. And if we have an exact couple, there's always going to be an associated spectral sequence, so that the E1 PQ term is given by BPQ, and the differential is induced by composing del with I star. So the next construction, this is actually like, I can't really give all the details of this because it involves some kind of like technical things in abstract homotopy, but so the idea is that if I have a simplicial model category with underlying simplicially enriched category M, so in this case, we could look at our simplicial enriched, we can just imagine this as being our simplicial enrichment of spaces, along with the usual model structure on spaces, which where I guess weak equivalences are basically maps that induce isomorphisms of higher homotopy groups. And suppose that we have some reedy fibrant simplicial object in this. So recall that a simplicial object is just a functor from, in our case, it's going to be a functor from delta op to spaces. We usually call such a thing a simplicial space. Then associated to this simplicial object, we have the space of n cycles, which is kind of the intersection of the kernels of maps from xn to xn minus 1. And then we have for basically all the face maps xn to xn minus 1. And then we have our n chains, which is the intersection of all face maps, of the kernels of all face maps for I greater than 0. Now, we have associated to this a fibration sequence of simplicial sets. And what this means is that we kind of get this long exact sequence of higher homotopy groups from this. The fact that this is a fibration sequence is kind of a technical thing that kind of follows from the tensoring of the reedy model structure of simplicial sets over the reedy model structure. But that's sort of, but we get an exact couple from this. And to explain kind of what these things are, the map IN is just the inclusion of the n cycles in the n chains, and the map del n is just basically it's induced by applying the face map D0 to get an n cycle from an n chain. And you have to do a little bit of work to just show that, in fact, if I apply D0 to n chain, I get an n cycle. So the long exact sequence of homotopy groups, we can kind of arrange these in an exact couple. And the map del will be kind of will kind of be induced by the boundary map there. And the map delta will be induced by the boundary map, and the map del star and I star are kind of induced by these IN and del n's. So we have a vertical and a horizontal grading here. So horizontal grading we can think of as corresponding to Zn of x star as our choice of Zn. And our vertical grading is based on the choice of homotopy group we're interested in. So that, and the map del, because it's the boundary map of a long exact, the map delta, because it's the boundary map of a long exact sequence, decreases the vertical grading by 1. And the map del star, the vertical map, decreases the horizontal grading by 1. Then we get the spiral spectral sequence, which basically computes the higher homotopy groups of the space of maps. So M you can just think of as just our usual space as topological spaces with its usual simplicial enrichment. So it computes the maps from Y to the geometric realization of this choice of simplicial object in spaces. And a geometric realization is kind of a homotopy colimit, which means it's a kind of colimit that somehow is defined in a way that it respects weak equivalences, or it respects, like, I guess, maps that kind of induce isomorphisms of higher homotopy groups. And this spectral sequence gets identified with a very general construction in algebraic topology called the Bousfield-Friedlander spectral sequence of a simplicial space. And in fact, a lot of important spectral sequences in algebraic topology can be expressed as Bousfield-Friedlander spectral sequences. So, I mean, my next kind of part of the talk that I could have talked about is I can talk about how we can kind of describe the differentials in this spectral sequence in terms of these operations, in terms of some kind of operations, like we've described, like Toda brackets or these type 2 operations. Well, they're a little bit different, but
I'm not telling you what to do, but I think skipping anything with spectral sequence is always a good idea.
Okay.
They're just, I mean, whatever. Unless someone wants to, I mean, what else is there? You have a lot more slides to go.
I do have a lot more, but I have something about how you can think about the higher operations in a quasi-category or simplically enriched category, the type 2 operations. But what I would like to do very quickly is I would like to mention that actually this description of the spectral sequences, actually the description of the spectral sequence, the way that we prove this theorem that I mentioned before about higher homotopy groups is like generation under these operations is actually proven using kind of a spectral sequence thing, a description of filtration in spectral sequence. So the idea is that there's kind of this, so we have this E infinity Pn thing in our spectral sequence, and then we have a map down to the thing that we're interested in computing, which are these higher homotopy groups of spheres. So the image, so basically the thing is that the map down to this kind of higher homotopy groups, these higher homotopy groups we're interested in computing from the terms in the spectral sequence is actually given as the value of a higher homotopy operation associated to a certain diagram, which I've depicted here. So that is basically how you prove the theorem about, and this is how you kind of prove that we can kind of generate these higher, that we can generate homotopy groups of spheres under these higher operations, these type 2 operations I mentioned, is using this kind of theorem relating the filtration in a spectral sequence to higher homotopy operations. And this is a value of a type 2 operation, which is kind of the thing I defined in terms of the hexagons and the permutahedron and stuff. So, I mean, I can talk about how I can define sort of versions of type 2 operations in a quasi-category for the rest of the talk, if that's what you'd be interested in.
What's our choices?
So the choices was to go in more detail about the differentials and spectral sequences,
Yeah.
or to talk about how we can do type 2 operations in quasi-categories where the composition is no longer kind of like strict like it is in a simplicially enriched category.
I personally prefer the second, but anybody else has an opinion that's more important than mine.
I vote 2 as well.
Yeah.
Okay. Okay, so I'll talk about quasi-categories now. So a quasi-category is a simplicial set such that we can find lifts for all inner horns. Every con complex is a quasi-category. So, and the nerve of a category, which was something I defined before, is also a quasi-category. The vertices of a quasi-category, so we think of the vertices of the quasi-category as objects. And for each pair of vertices, we have a con complex of morphisms. And in the Joyal model structure, there's basically the homotopy type of the quasi-category is determined by its path category and these con complexes of morphisms, which kind of play the same way that the simplicial enrichment does. Yeah. So quasi-categories allow us to talk about right homotopies of one simplices as well as compositions of one simplices. So the idea is that if we have a 2 simplex with boundary as depicted, then we say that alpha and beta are right homotopic. We say that H is the composite of G and F if there exists a 2 simplex with boundary as depicted on the right. And the thing to note is that this composition operation is only well defined up to homotopy, in the sense that I've defined, in the sense of having this kind of, in the sense that I've defined. So the path category of a quasi-category has as its objects vertices, and as its morphisms between X and Y, homotopy classes of one simplices. So is there any questions about this definition? I guess in the picture, the 2 simplex on the left represents the homotopy, and then the 2 simplex on the right kind of represents the fact that H is the composite of G and F. The thing is that so compositions are kind of well defined only up to this notion of homotopy in a quasi-category, but which makes kind of defining these Toda things a bit difficult, or these higher operations a bit difficult. So to kind of make more sense of this, we can work with minimal quasi-categories. So minimal quasi-category is a quasi-category X such that any 2 n simplices homotopic relative to the boundary are equal. And every quasi-category, there exists a Joyal equivalence with X from X to some minimal quasi-category. And we can also produce in a highly non-unique way an embedding of a minimal quasi of the minimal model of X into X. So the idea is that the reason why we want to work with minimal quasi-categories is that the composition operation, which is usually only associative up to homotopy in general, becomes strictly associative in a minimal quasi-category. So we should be able to define homotopy operations in a quasi-category because we've been able to we can define them in general in terms of simplically enriched categories, and kind of quasi-categories and simplically enriched categories are both models of infinity one category theory. So we ought to be able to give an intrinsically quasi-categorical description of things that would like capture our notion of type 2 higher homotopy operations. So we have in a quasi-category, an arbitrary quasi-category, we actually have fiber sequences, which we can actually form the end chains and end cycles and so on and so forth. And we actually have this analog of the spiral spectral sequence, which is the thing that you need to use to prove this kind of theorem about how higher homotopy operations generate generate homotopy groups under so yeah, but anyway, so basically to define a threefold operation in a minimal quasi-category, we start with a restricted simplicial object in P of X of the type that we had before. So P of X is the path category. And we choose witnesses for the compositions of various maps. So that those are like two simplices that exhibit the composition in the quasi-category. And we can kind of arrange these guys together as depicted. So the superscript says that it's like starting from x2. So like the superscript says that what xi it's starting from. So for instance, like d2j is starting from x2, d1j is starting from x1, d superscript 1 subscript I says that it's starting from x1. So we get here, we get the include. So basically what we get is we get the inclusion of two faces of a 3 simplex into the 3 simplex. This is actually an inner anodyne map, which means we can always fill this in a quasi-category. And so we get a sort of a resulting 3 simplex. Basically, so is there any questions about this particular diagram here?
Go.
Okay, so we get the back face of this guy, gamma ij. So what we do is we get these gamma ij, gamma j minus 1 i's, and then we have a degenerate face. So this is like an inner horn. So then we glue this together and we get, so then we fill this in our quasi-category because we can always fill in inner horns in a quasi-category. And then the bottom face of this is something we call the canonical homotopy between so-called canonical homotopy. And then the way that we define our threefold operation is we just kind of arrange these canonical homotopies in a hexagon kind of pattern. And we can show that this actually gets that I'm using this equivalence between simplically enriched categories and ordinary categories. Simplically enriched categories and quasi-categories. This actually gets identified with the operation I defined before. One kind of comment is that's important with this is that so what we did when we first defined our kind of type 2 operation is we made some kind, or our Toda bracket for that matter, is we made some kind of choice of homotopies between various composites. But this actually does not really like make sense in the quasi-category world. So we didn't do it in the exact same way because every composite in a quasi-category world is only defined up to homotopy. So so it doesn't really make sense to do that. But this actually does recover the operation that we've defined before in the quasi-category world. And this can actually be sort of like viewed as like an obstruction from like lifting something from like a diagram in the path category of X to like a diagram in X, an actual map of simplicial sets. This thing, the vanishing of, I guess, the element of the loop in, I guess, the element of pi 1 in the space of maps corresponding to this. That's what I have so far with this talk. are there any questions?
There it is.
So,
So you finished your thesis, or you finished your thesis? This is a postdoc, right?
Yes. Yes.
so this is all really neat. There's obviously a lot you couldn't explain, and I want to thank you for giving overviews of things like quasi-categories along the way. But do you have anything you'd like to advertise, like a portion of this up on Archive or something, so that people could dig in if they're interested in this?
We're not quite on Archive yet, but we'll probably be there in a few months.
Okay, cool. Thank you. Yeah.
But yeah, I mean, so I guess like the sort of the real novel part is I guess that my one kind of comment is that the novel part of this will be the quasi-category thing, and there's also the description of differentials and spectral sequences, which was kind of a bit, which, as you said, you didn't really want me to go into, but that's novel. That's one of the novel parts that I did, like this kind of type 2 operations. Like I guess my postdoc supervisor has done this kind of stuff, has done those before. It's just like, I guess in our paper, we're kind of, so yeah. So the stuff about differentials and the quasi-category stuff is new, but the type 2 operation was something David had done before. And the Toda bracket is probably from like 1960 or something. Yeah. So any further questions or no?
Just had a comment to another sort.
Mhm.
As it turns out, you know, it's been better now, but there was at City University was meeting on the Wednesdays too. There was another group that Gershom and I had where there were topologists who were interested in exactly homotopy groups of spheres, etc. So
I was actually supposed to speak at that seminar, but because of the whole thing, it got canceled. The thing that happened, it got canceled, and I didn't hear anything about.
So you know all about that, yeah? From Mahmoud, he didn't. Yeah, canceled it a month ago, and we'll see what happens maybe next year.
I did give a talk at a topology group in Virginia. That's except I went faster, obviously, because they're like topology experts. So I didn't talk about groups of spheres. Basically, like the second half of this talk would have probably been what or the second, like basically. I mean, I had to like not many of them know about Toda brackets, so I had to like that's not that well known unless it's like these days. So I had to go through that.
Sure.
But like the first half of the talk would have been considerably shortened for them. So it was like an hour talk instead of an hour and a half. But basically roughly the same. And I went into the gory details of the spectral sequence and how I can. But I guess the idea of I should actually mention, and this is kind of an important thing. Is that describing the differentials in these homotopy limit spectral sequences or homotopy colimit spectral sequences is very difficult. And these higher homotopy operations, which involve kind of like picking homotopies between maps and patching them together, is like a very explicit way of like describing those. So you can get some good theoretical utility, I think, out of that. Because some of these spectral sequences that they use is like notoriously difficult to compute with.
Sure.
Kind of.
Well, yeah, and then in the situation, well, that's hard. I'll need another sequence to just get a page of that, and yeah.
Yeah. But my thing was that I was going to actually literally describe the differentials in terms of higher homotopy operations of a slightly different shape. Like instead of getting hexagons, we get a product. We get like a product of a hexagon and a unit interval or something like that, and so on and so forth. And that was but that's that was kind of but this was kind of like part of the novel stuff that I was sort of doing with David, was the spectral sequence stuff. Thank you very much for inviting me. I really appreciate.
Hey, thank you very much. And I'm going to be putting it up, and I'll send you a link of where it is, and as soon as I figure out how to get it.
This was a good talk. Thank you.
Thank you very much. Okay, I'm going to stop the recording.